Hello everyone, this is going to be the last video where I will talk about how to extend the Hilbert transform to LP functions and thus completely finish off our goal of proving that, at least for Schwartz functions, the Hilbert transform is certainly bounded in the LP norm in the sense that, the sense that we mentioned that for a Schwartz function f, the LP norm of the Hilbert transform applied to f is less than or equal to a constant times the LP norm of f, where the constant is independent of f. Okay, right, and so remember what we had last time. We carefully proved this, and it took a lot of work, but we did it. So last time we had basically the weak 1-1 type inequality that we needed for the Hilbert transform. Not quite, and we still have to do a little work to actually use the Marcinkiewicz interpolation theorem. So remember, if f is an L1 intersect L2 and lambda is positive, then we have this weak 1-1 type inequality, where in particular C is independent of F. Okay, so there is some C independent of F in L1 intersect L2 where this is true. Okay, so the question still remains, how do you define the Hilbert transform even for an L1 function? It's not necessarily defined. And so what we have to do is, and there's just really no way to avoid this, this is a pain in the ass, but this is just what we have to do is we have to use this to extend the Hilbert transform. So I'll write it like this, give myself some more room. So yeah, we have to use this here to extend the Hilbert transform to L1 functions. And the key here is the following, which I don't think is usually talked about in 510A, but yeah, that's all right. It's probably usually something we would do if we had more time. So the following lemma holds, and I'll basically prove half of it, leave the other half for the last homework. So let's say we have a sequence of measurable functions. Script M is a set of all measurable functions on the real line, since we're dealing in dimension 1. Okay. So let's suppose that the sequence is Cauchy in measure. What does that mean? Well, for any lambda and epsilon positive, there exists n depending on epsilon and lambda, where m is bigger than n. It's basically what you would expect is as a Cauchy in measure version of convergence in measure. So I should be able to squeeze this in. Okay, so the measure of this set here, x and r, where gn of x minus g m of x bigger than lambda is less than epsilon. Okay. So let's suppose that this is true. And again, if this is true, if what I'm going to put in red is true, we say that Gn is Cauchy in measure. Okay. MEAS, that's a U. Anyway. So if this is true, then there exists a measurable G where Gn converges to G in measure. And let me just remind you of what that is. And that means for any lambda bigger than 0, this limit here is 0. So the limit as n goes to infinity of the measure of the set g of x minus gn of x lambda. Right. So this limit is 0. Right. No uniformity with lambda. Just for any fixed lambda, this limit is 0. And actually, as part of the proof, there is a subsequence GNK that converges pointwise almost everywhere to G. We to some degree don't even care. It's just part of the proof. We're going to need that. Okay, so right, and it's a bit of a tricky proof, but I think these details are important to understand. So, all right, so let's start off the proof. Okay, right, so basically, step 1 is to find a measurable function g and a subsequence g and k, and I'll just use big N. Why not? Doesn't really matter. Where g and k converges to g, sorry about that. Pointwise, almost everywhere. Okay, so I should say this lemma here is usually in books on on harmonic analysis. This lemma is either just completely swept aside. A lot of books will be like, well, okay, so what this in blue here is true. So the Hilbert transform extends to L1, basically without, they'll just implicitly assume this is true without mentioning anything, why, how, or rhyme or reason. Yeah. So I think it's worthwhile to really carefully get under the hood and see what's going on. Okay, so how do we do this? Well, this is not too bad. So in the definition of Cauchy in measure, we're going to let, for each k, each natural number k, we're going to let the epsilon equal lambda equals 2 to the minus k. So what do I mean? What I mean is we're assuming, and I should maybe mention first that we're going to apply this lemma to the Hilbert transform. This inequality here in blue is going to mean that basically for f in L1, and if Fn converges to f in L1, where Fn is L1 intersect L2, then Hfn is Cauchy in measure, and hence we can take the limit and it'll converge to something and measure. We'll get to that moment, but anyway. So yeah, so here I'm basically saying, well, I'll do this in a different color. So we're saying epsilon and lambda are 2 to the minus k. So maybe make this yellow. Okay, so let's say there's some nk where this is true. 2 to the minus k. So quite a bit of flexibility in this definition of Cauchy in measure. Okay, Right, so this is exactly this is exactly what's true, okay? Right, okay. Okay, so, right, so, yeah, so let's say actually, we're going to pick NK. So maybe I don't want exactly this. I guess I'll still keep it like this. Sorry about that. So let me just keep it the same. Here, 2 to the minus k, 2 to the minus k. Move this over a bit. Okay, so I actually want to pick nk larger than this n here. So I'm going to, yeah, I just want to pick some n depending on k. It doesn't even matter what it is. Bigger than this n here that corresponds to Cauchy measure. And without loss of generality, I can assume that n1 is less than n2. I can assume that these are increasing. Because I can always, I can always make this, force it to be larger, take the maximum of everything, make, let's say, nk the maximum of all the n's up to k minus 1 plus 1, something silly like that. Okay, so let's define this relevant set here, ek, to be set of all x where g and k plus 1, g and k bigger than 2 to the minus k. Okay, so right, so nk plus 1, well, is bigger than nk. Nk is bigger than this n 2 minus k, 2 to the minus k that comes from Cauchy measure. Okay, so in particular, this here is true. Okay, so if you remember from 510a, you could probably see where this is going via Borel-Cantelli. It's one of my favorite little lemmas from 510a. Okay, so right, forget about anything sum. What we have here is that the measure of ek is less than 2 to the minus k. Okay. So this is less than or equal to 2 to the minus k, and that's finite. What does that mean? By Borel-Cantelli, for almost every x, there exists kx. So first of all, I should say, what does exactly Borel-Cantelli tell me? If I have any sequence of measurable sets, ek, where the sum of the measures is finite, then almost every x belongs to at most finitely many of the EKs. Okay? So for almost every x belongs to finitely many of these EKs. what does that mean in math terms? Well, that just means there exists kx, make that a capital K, a natural number kx, where if k is bigger than this natural number kx, maybe I should put it like this. So this implies x is not in EK. Again, all I'm saying is for almost every x belongs to at most finitely many of the EK. So eventually x is not an EK for large enough k. That's all I'm doing is quantifying this. And this for large enough k absolutely depends on x. We're not claiming any uniformity here. Anyway, so what does that tell me? Okay, so I claim that GNK converges pointwise to, I claim that GNK is Cauchy, a GNK of x for almost every x is Cauchy as a sequence of real numbers or possibly complex numbers, whatever. Okay, so let's show that. Okay, so, well, if we want to show that we have for each x, a sequence of Cauchy, a Cauchy sequence of real numbers, complex numbers, we start off with an epsilon. Okay. So, again, there's no issue with bumping up kx. Kx could be, we can make it as, we can make it larger than this thing here. So that loss of generality, let's assume kx is so large that this is less than epsilon. Okay, so, right, so if n and m are bigger than kx, and let's just, without loss of generality, assume n is bigger than m. Otherwise, just erase and change notation. Okay, so if n and m are bigger than kx, then let's look at, well, obviously I have to look at this if I want to prove that for all such x, GNK of x is a Cauchy sequence of complex numbers. So this is kind of reminiscent of proving that L1 is complete, or rather that if you have convergence in L1, there's a subsequence that converges pointwise almost everywhere. Okay, so just do, well, this is going to be fairly trivially equal to the following telescoping sum here. G n k plus 1, G n k of x, smash in absolute values. Oops. And yeah, you should be able to see where this is going. In red here. So the point here is, well, both of these are going to be bigger than k, or rather, sorry, that's not what I wanted. K and k plus 1 are both bigger than kx. Because certainly k is, well, it's certainly bigger than m. Right, sorry. K no matter what k is, it's certainly bigger or equal to m, and m is picked larger than kx. So for each k, both of these are true. Okay, so what does that mean? That means x is not in ek. Well, what does it mean for x to not be in ek? Well, so ek complement, same thing as x is not in ek. X is not in ek is saying x is an ek complement. Well, that just means, get the damn eraser, there we go. That means it's less than or equal to. So ek complement is this here. Okay, so because x is not an ek, right, or rather x is not an ek and x is not an ek plus 1. Well, actually, sorry, all we need is ek. Sorry, we don't even need ek plus 1 here, really. Maybe it's just a little confusing. So, right, so get rid of this. Sorry about that. So k is bigger than kx because k is bigger or equal to m. So x is not an ek because x is not an ek. This x is in this set. Okay. So plug that in. Let's go back to regular color. K equals m to n minus 1. So this is going to be 2 to the minus k. And, well, yeah, so you can, yeah, so this is going to be less than or equal to basically 2 to the minus m plus 1. And actually, sorry about that, I actually want 2 to the minus kx plus 1 to be less than epsilon. Not a big deal, just so that I get epsilon. All right, well, m is bigger or equal to, actually m is, what I had was fine. 2 to the minus kx is perfectly fine. M is bigger than kx, so this is less than 2, less than or equal to 2 to the minus x. That's less than epsilon. Okay, so what did we prove? We just proved, I'll put this in orange. So for each, or for rather almost every x, there exists a natural number kx, where if n and m are bigger than kx, then g and n minus g and m is less than epsilon. Okay, and that means exactly that this is Cauchy for any such x. And to make this clear, this is a subset of complex numbers. All right, so, well, we know Cauchy sequences of complex numbers converge to some complex number. So let's say g of x is this limit. Okay, so we have carefully proven that there is a subsequence of the GNs that converge pointwise almost everywhere to some measurable function. I mean, we know pointwise convergence of measurable functions are measurable, so there's really no nothing to prove. Yeah, this is measurable. Okay, so that at least completes step 1. Step 2. Well, really, step 2 is Gn converges to G in measure, and that is going to be for homework. So I don't know if this counts as a legitimate proof. Just kidding. Proof is homework, but anyway. Okay, so let's put this to good use. Okay, right, so, yeah, so yeah, the rest of the proof is for homework. All right, so now let F be in L1, Fn converge to F in L1, and let's say Fn is an L1 intersect L2. Okay. Okay, so we obviously know the Hilbert transform is linear. Okay. All right, so let's just well, it's pretty trivial that HFN is Cauchy measure. Why? Well, this here, HFMX, bigger than lambda. Let's say lambda is positive. And yeah, just to remind you, it's absolutely trivial. So this is going to be equal to Fn minus Fm of x. Okay. Fn minus Fm is certainly an L1 intersect L2. Okay. So this is going to be less than or equal to this constant Fn minus Fm 1 over lambda. Right, and let's just say this is less than epsilon for nm bigger than some big N. All you do is pick big N so that this here, yeah. So let's write that down, pick big N for N. M bigger than N implies Fn minus Fm is less than lambda epsilon over C, I think. Yeah, that kills off this lambda. We get rid of the C, and then we get an epsilon. Matters, but what's an epsilon? Right. Okay, so this is Cauchy measure, HFN. It's a little bigger. This. Okay, right, so HFN. Okay, so, right, so we know, and let's denote this limit by H tilde F. Most authors just say, define the Hilbert transform on L1 to be this limit, which is fine. I mean, I did that with the Fourier transform. I didn't use new notation for the Fourier transform on L2, even though it is the unique extension from L1 intersect L2 to L2. But anyway, yeah, so define it to be this limit here. Maybe I'll write it like this. And to clarify that we have convergence is in measure. We do have, for some subsequence FNK, pointwise convergence. We carefully proved that a moment ago. Okay, but yeah, so we really more want convergence in measure, and that's part of the lemma. which is for homework. Okay, so just a few things here. Okay, and I'll just prove this to make sure we're all on the same page here. H tilde is the unique linear, and you can check this is going to be linear. You know, just really nothing to that. Linear, yeah, so I should say before I do anything, I'll get rid of this here. So I'll leave it for a homework exercise. It's really not that hard. That H tilde is going to be genuinely weak type 1, 1. So for any F in L1, you can use this fact here to get that the measure of X, where this is true, is less than 2C. And the 2, you can actually get rid of 2 if you're really careful, but it's a lot easier to prove this fact with the 2 here. And so C is exactly the same C as here. Okay. So yeah, here, or rather, well, yeah, it's the same. C, so it's basically the same conclusion here, except the 2 here. And again, as I said, you can work very carefully to get the same constant. It's just, for homework, I'll have you prove that instead of C, you have 2C. Make life a lot easier. Okay. Right, so in other words, H tilde is, in fact, weak type 1, 1. Okay, that's great, because now I finally have a weak type 1, 1 operator. And just to, you know, make sure we're all on the same page here, I want to prove, kind of actually gives you a hint as to how you would approach the previous homework. This is the unique linear extension, and as I said, I'm not going to have you collect. I'm not going to collect this, but H tilde is linear because the Hilbert transform is linear on L1 intersect L2 because Fourier transforms are linear. So yeah, nothing really to that, not much to that. It's unique linear weak 1, 1 extension to L1. And proof. Okay, so how do we prove this? So let's say we have something else, H prime, BH on L1 intersect L2. So when I say extension, I mean from L1 intersect L2. Let's assume H prime is linear on L1. And let's assume H prime is weak type 1, 1 on L1. Okay, right. So let's say lambda is positive. All right, so let's do something pretty trivial. Let's just use triangle inequality. So, well, not that it matters, but you want a tilde here. Okay. So what I want to do is I want to prove that the set of all x where this is true is 0. And then I can just, as we've done before, as you did in 510a, probably dozens of times, that means the set of all x where h tilde f of x minus h prime f of x is positive is 0. That has 0 measure. And of course, when I say unique, I mean up to a set of measure 0, sort of, or rather, we're going to prove that h tilde f is h prime of f. So rather, let me maybe put into words what I just said. And to clarify, let's say f is an L1. So what I want to show is that this set here HF tilde minus H prime F lambda. I want to show that this is 0. And as we've done before, this implies countable subadditivity of measure that h prime of f is h tilde of f almost everywhere. All right, so let's do what we've done many times before. Just use triangle inequality. H tilde of f of x minus h prime f of x is going to be less than or equal to. We don't have to be super careful with our triangle inequality, or super subtle rather. Well, by definition, HFN, H tilde f rather, is the limit of HFN. Where by limit I mean convergence and measure. Okay. Well, HF is H prime F, or HFN is H prime FN because they're the same on L1 intersect L2. Okay, so maybe I should say let FN converge to F in L1, and this is in L1 intersect L2. Sorry about that. So that's what Fn is. Fn converges to F in L1, and Fn is an L1 intersect L2. So H is H prime on L1 intersect L2. So HFN is H prime Fn minus H prime X. Okay, so that means this measure here that I want. So it's basically the same thing we did for the Fourier transform, proving uniqueness. It was a homework that you prove uniqueness of an extension from this dense subset L1 intersect L2 in the Hilbert transform case, except we're dealing with measure, so it's a little trickier, but not much. Okay, so so this is going to be less than or equal to, give myself plenty of room here. Yeah, I'll start here. Well, so as we've done many times before, thanks to this triangle inequality, it's going to be this, not with a lambda, but lambda over 2. Really have to squeeze this in, but I'll try and do that. Okay, and same thing here, lambda over over 2. And I'm going to use the fact that H prime is linear. So H prime, this is good because it's going to allow me to fit this in a little better. Sorry, there is no M here. I meant, there we go. Right, this is bigger than lambda over 2. Okay, well, there is no n here, so I can just take the limit here. Really taking lim sup, because we a priori don't know that the limit exists. Okay, well, this, this is convergence in measure. HFN converges to H tilde F in measure. So by definition of convergence in measure, I wrote down the definition, I don't know, 10 minutes ago, 15 minutes ago. I'll just go back real quick. Where's the definition? Yeah, so for any lambda positive, this limit here is 0 if G n converges to G in measure. Well, lambda over 2 is certainly positive if lambda is. So then this limit here, because HFN converges to H tilde F in measure, converges in measure, so this is 0. I'm going to use the weak type property here. Okay, so this is going to be less than or equal to 0 plus this lim sup here. So this is going to be C for some C independent of F over, well, sorry. So let me erase this. So it's the C from the weak type definition. Because I had a lambda over 2, it flips to be 2 over lambda. F minus Fn. Okay. Again, just H prime, we're assuming is weak type 1, 1. Well, this is obviously 0. And lambda could be itty bitty, teensy weensy. So that this could be huge. This could be something like 10 billion, 100 million, billion, whatever. But as n goes to infinity, because lambda is fixed, no matter how small it is, this is still 0. So this is 0. So yeah, for any f in L1, H prime f is H tilde f almost everywhere. So that takes care of uniqueness. And again, this is kind of hinting how you're going to prove that actually H tilde is weak type 1, 1, i.e. how you're going to do this homework. All right, so let's finish things up here. So that takes care of this proof. So the extension is unique. So we have to do one more thing here to invoke the Marcinkiewicz interpolation theorem. And, you know, I did mention this is a pain in the ass, I think. If I didn't, well, it is. I'm not going to lie. But so remember what we need for the Marcinkiewicz interpolation theorem. We're going to use it between 1 and 2 because H tilde is weak type 1, 1. H tilde is trivially weak type 2 because it's bounded on L2. It's an isometry on L2. But we need then, if we're going to use P equals 1 and P equals 2 in the Marcinkiewicz interpolation theorem, we need a linear operator defined on L1 plus L2. Okay, so what we need to do is extend the Hilbert transform to L1 plus L2 rather to invoke the Marcinkiewicz interpolation theorem. So in particular, for lack of a better thing to call it, let's say H tilde tilde. most authors just basically just use H again. Most authors actually don't even mention this step here, but really you do need to do this. So let's define H tilde tilde on L1 plus L2, mapping to measurable functions. So let's say let this be H tilde tilde, apply to some F in L1 plus L2. Right, and this is going to be, these are two tildes. Well, let's just say it's H tilde F1 plus H F2. Here F is F1 plus F2. And here this is in L1, and this is in L2. Okay. So yeah, let's just quickly prove this here. That this is, and whenever you define something on L1 on any, the addition of two vector spaces, you have to check that this is well defined. Okay. That it doesn't depend on how you write F as a sum of L1 and L2 functions. All right, like I said, this is an easy proof. Right, so let's write a function in two different ways. So let's assume that F0 plus F1. Let's say we're writing F as F0 plus F1 and G0 plus G1. And again, this is in L1, this is in L2, this is in L1, this is in L2. Well, actually, sorry, I did 1 and 2, so let's also do 1 and 2. Sorry about that. Not that it matters all that much, but just to be consistent. Okay, so yeah, so we want to prove that so basically we're saying this is two different ways of writing my function f in L1 plus L2. So we want to prove that it doesn't matter which pair of functions f1, f2 versus g1 and g2 we use to define h tilde tilde of f. So we want to prove that, well, if we use this one, it's going to be let's go back, it's h tilde f1 plus h f2. We want to prove that this is going to be equal to h tilde g1 plus h g2. All right, so why is this true? Well, so first of all, we fairly trivially have, well, not fairly trivial, very trivially, just subtract off f2 and subtract off g1. f1 minus g1 equals f2 minus g2. Sorry, get that mixed up. It's g2 minus f2. Okay, and this says quite a bit, actually, in particular. So remember that G2 and F2 are in L2. Okay. So if G2 and F2 are in L2, subtract them, it's in L2. But F1 and G1 are both in L1, so the subtraction is in L1. So in other words, this is in L1 intersect L2. And same thing here. This is obviously in L2, but F1 and G1 are in L1, so this is also in L1 intersect L2. So what does this tell me? Well, this tells me that if I apply H to F1 minus G1, no issue here. This is an L1 intersect L2, so this is certainly well defined. This is going to be H of G2 minus F2. Well, we know H is linear on L2. It's absolutely well defined on L2. H is not defined on L1, and each individual F1 and G1 need not be an L2. F1 is an L1, G1 is an L1, so we can't use linearity and applying it separately. Okay, so we get this at least. Okay, on the other hand, H of, I have here, F1 minus G1. Well, that's going to be the same thing as H tilde, because again, F1 minus G1 is an L1. It's an L2 also. H tilde is an extension of H. Okay, so H tilde equals H for things in L1 intersect L2. So this is going to be H tilde F1 minus G1. Now H tilde is linear on F1, on L1. Both of these are on L1. So this is H tilde F1 minus H tilde G1. Okay, so what does this mean? This means H tilde F1 minus H tilde G1. We'll kind of go back here. Is HG2 minus HF2. So that means exactly what we want to prove. H tilde F1 plus HF2 is going to be H tilde down a bit. So yeah, very easy proof, but still, I want to go through it and make sure we're all on the same page here. HG2, and that's exactly what we want to prove. H tilde F1 plus HF2 is H tilde G1 plus HG2. Okay, so yeah, this is well defined. Okay, so, right. So, we have H tilde tilde defined on L1 plus L2. It's weak type 1, 1 because H tilde tilde is H tilde on L1, or for L1 functions rather. It's certainly strong type 2, 2 and hence weak type 2, 2 because H tilde tilde is H on L2. So we have by the Marcinkiewicz interpolation theorem that for any p between 1 and 2, we have this extension, okay, is going to be, and arguing as we did many times, this H tilde tilde is going to be the unique bounded linear extension of the Hilbert transform to LP. Is less than or equal to, I'll just write down exactly the bound you get from Marcinkiewicz interpolation theorem. Because it's really good, useful information, as I'll mention in a second. So, it's 2 times p to the 1 over p. It looked a little funny. So here p0 is 1, so it's 1, 1 over p minus 1. P1 is 2. Okay, so this is a little funny here. We kind of get blow up as p approaches 2, and we'll fix that in a moment. Okay, so the Hilbert transform is an isometry on L2, and we had a C independence. Well, we had a C. This C is from the weak type inequality, so it's just going to be well, just some C independent of P here, because the weak type bound. Yeah, that's it's just some constant. So right. So if you check, you're going to get C independent of P, and so it's F to the LP. So maybe sorry, I should pop in F here. Okay, so in particular, so in other words, for F, if F is a Schwartz function, we get, at least for P between 1 and 2, we get exactly what we want. Right, I'm not going to repeat everything, but certainly a Schwartz function is in, well, L2, so H tilde tilde F is H F, just writing it as 0 plus F. 0 is an L1, F is an L2. Okay, so yeah, we get P. This is just everything here. Yeah, I'll put this in red here. Okay, so let's finish things up by looking at the Hilbert transform on LP for P bigger than 2. And the technical issue, as always, is how to even define the Hilbert transform on LP when P is bigger than 2. Okay, and for objects that are like the Hilbert transform, this is actually a pretty subtle question, and a lot of authors basically broach this using the theory of distributions, which I've really tried to avoid like the plague. Not that they're so difficult, but I feel like at this level it's unnecessarily, they're unnecessarily complicated. So we get a little lucky in that, at least for a Schwartz function, we have that HF as an LP if F is a Schwartz function. Okay. And here, really, P can be anything between 1 and infinity. Okay. And the reason is, well, it's pretty straightforward. The reason is basically this formula that we have for the Hilbert transform for a Schwartz function. Okay. So roughly speaking, well, there's no issues with y small because f is differentiable for every x. And because f is a Schwartz function, you have a lot of decay. So I mean, I don't want to give too many hints, but yeah. So you'll use a combination of mean value theorem, Holder's inequality, or maybe not. I don't know if you need. I have to double check if you need Holder's inequality, but Young's inequality, particularly this term here. Yeah, so it's pretty straightforward. So let's put this to good use. Okay, to extend the Hilbert transform to LP functions in general when P is between 2 and infinity. Okay. So in particular, this we're allowed then to use duality. Okay. And in particular, what I really want to do is take this H tilde tilde and extend it to LP for P between 2 and infinity. Okay. Right, so, this is true for any P, but we've already basically handled P between 1 and 2, so now I want to handle P between 2 and infinity. All right. Right, so this is going to be, because we know, well, this really is HF, because F is a Schwartz function, so this is really HF. Remember, H tilde tilde does extend it does extend the ordinary Hilbert transform, particularly F is in L2, so H tilde tilde F is HF by definition. Okay, so this is going to be sup of all G in L P prime equals 1. And because we know that this is an LP, well, we can really just take G to be in a dense subset of LP prime. Let's say it's a Schwartz function. Okay. Okay, so like I said, H tilde tilde is really H on particularly L2 functions. F is L2. So this is going to be by duality. It's really, well, it's really an integral, but it's just more convenient to write it as, an L2 inner product. So when I say L2 inner product, I really mean HF of X, G bar of X, dx. Okay. Right. So let me erase this. So yeah, there's no Hilbert spaces here. So I mean, technically, well, yeah, technically HF is, I guess, an L2 and G is an L2. But anyway, I'm really using just LP duality via the usual pairing. Right. So let me erase this. Okay. So, right. So you can check actually, because really, I mean, so I guess this is not, I'm not really being inaccurate when I say this, but, because F and G, HF is an L2, G is an L2, so this duality pairing really is the actual L2 inner product. So yeah, because this is an actual L2 product, you can actually check that as an L2 adjoint. Remember, H is an isometry on L2, so the adjoint exists. But as an L2 adjoint, H star is just going to be minus H, or in other words, H is its adjoint, except a minus sign. Okay. All right, so, and there is some subtlety with dealing with adjoints for Banach spaces in terms of all this. I'll maybe mention a little bit more about this later. That's a bit subtle, not necessarily for the Hilbert transform, but in general for integral operators that behave like the Hilbert transform. All right, so yeah, we can take the adjoint, but that just becomes minus, so bring it over. So what is this? This really just becomes this supremum here, G LP prime equals 1. Running out of room here, but this tiny thing is just saying G is in a short space right here. And this I'll leave. It's a very easy homework. That as an L2 operator, the adjoint is H minus H. So this is going to be H G F L2 All right, so now you do just Cauchy-Schwarz, or sorry, Holder's inequality, because again, remember, this is really just this integral here, h g x f bar of x. So we can certainly use Holder's inequality. Well, this is just going to be, I'll just write the soup here. Should be able to squeeze this in. G is in the Schwarz space. That, about that. Okay, so this is going to be, I have to squeeze it in, but that's fine. So HG L P prime F L P. So it's HG P prime F L P. Okay, well, so the Hilbert transform, so this really, the Hilbert transform is H tilde tilde, again, on the Schwarz space, and this H tilde tilde we know is bounded on LP prime, because if P is between 2 and infinity, P prime is between 1 and 2. So this is less than or equal to this operator norm here, from LP prime to LP prime, well, times norm of G, which is just 1. Right. So yeah, like I said, this is just 1, so let me erase it. I mean, there should be a supremum here, but because it's 1, you can get that, and I'll write this back out again in a second. So this LP. Okay. So in other words, H tilde tilde, at least for Schwarz functions, which are dense in LP, and let me actually write out the estimate we got here, because it's important to do that. P prime 1 over P prime, that. So it's 1 over, remember it's P prime minus 1 plus 1 over 2 minus P prime. 1 over P prime. Okay. Times the LP norm of F. Okay. Okay, so what does this finally tell us? This tells us that, well, we can play this extension game again. H tilde tilde extends to a unique bounded linear operator on LP for P between 2 and infinity because of this estimate here. Okay. So, right, but everything is an extension of just the Hilbert transform itself. So, final conclusion is that H extends boundedly to LP. Okay. Okay. So a neat, curious fact here, just from this here, and well, I don't have it here, but remember we got the same bounds here, except it's P instead of P prime when P is between 1 and 2. So we actually get the asymptotics, which is often, interesting and useful, really for any bounded operator on LP in any setting where it's not bounded for kind of your endpoints. You ask the same kind of question for different operators, let's say even on holomorphic function spaces. What kind of asymptotically is the behavior on the endpoints? So in particular, we have, and when I say H, I mean the extension to LP. This is big O of 1 over P minus 1, so it asymptotically behaves like P minus 1, or rather 1 over P minus 1 as P approaches 1 plus. And from this here, you can check P prime is just P over P minus 1. That as P goes to infinity, this behaves asymptotically like P. Okay, and there is some issue here, at least from the Marcinkiewicz interpolation theorem bounds, and this is just a defect of Marcinkiewicz interpolation theorem, that we know the Hilbert transform is an isometry on L2, but in both of these bounds, the LP bound for this Hilbert transform extension, when P is slightly smaller than 2 and when P is slightly larger than 2, which is exactly right here, the bound seems to blow up. So it looks like we have a discontinuity for the operator norm as P approaches 2. Well, that's not true. And in fact, you can do something silly like take the L, you can really pick any 2 points between 1 and 2 and to an infinity. I don't know. You can do the L3 over, you can interpolate between L3 over 2 bounds and the L3 bounds for this extension of the Hilbert transform, and use the Ries-Thoren theorem to get that there is absolutely no blow up. The operator norms for this extension are bounded between as we get close to 2, there is no blow up in the operator norm bounds. And I just picked 3 over 2 and 3 because why not? You really any fixed numbers between 1 and 2 and to an infinity, you can interpolate between those two using the Ries-Thoren theorem. I'll leave that for you to do.